Welcome back to the deep dive. We're really diving into something today that feels like it could genuinely shift how we think about AI learning.
hmm
There's this paper causing quite a stir, in the ML community.
Yeah, I've seen the buzz.
We're going deep on 2007.02092 energy-based transformers are scalable learners and thinkers. It's significant work from Alexi Gladstone and their team.
Absolutely. It's not just another paper.
Here, this feels less like an incremental step and more like, well, a bold rethinking of how intelligence, maybe even something like human reasoning, might emerge and scale up in AI.
Exactly. And what's so interesting, I think, is that it hits head on one of the really big challenges in AI research right now.
Which is,
How do we generalize this thing we call system two thinking? For experts like you listening, we're not just aiming for models that do one specific thing anymore.
no, the game has changed.
The real push is towards getting these complex, reasoning-like processes to just emerge. And here's the kicker: doing it only from unsupervised learning.
Wow.
That alone tells you how ambitious this paper is. It's really pushing the envelope on, self-sufficient AI that learns to reason without us explicitly telling it how to reason.
Okay, so our mission for this deep dive then is pretty clear. We need to properly unpack this core idea, these energy-based transformers, or EBTs. We need to get into their mechanism, really understand how they're claiming to pull off this unsupervised system 2 thing.
And then the results.
Yes. And then dive into the empirical results in the abstract, because they look pretty compelling, especially around scalability and how they perform across different types of data. That seems key.
Definitely. We'll break down the how and the why they call EBTs a promising new paradigm. Since you're all deeply into ML, data science, math, we'll jump straight into the technical meat.
Right.
Focusing on this novelty, this idea of getting sophisticated System 2 capabilities purely unsupervised. It's about moving past just pattern matching, towards models that can actually reason more generally. It feels like it could fundamentally change how we build intelligent systems.
Okay, great. But before we get into EBTs themselves, maybe let's set the scene a bit. Talk about the current landscape for System 2 in AI, because understanding the limitations really highlights why this paper is potentially so impactful, doesn't it?
Absolutely essential context.
Yeah, so we've all seen this explosion, right? These inference-time computation techniques. Things often compared to human system 2 thinking, that slower, more deliberate kind of reasoning.
Like chain of thought.
Exactly. Chain of thought, self-refinement, loops, and LLMs. They're hugely popular for boosting performance. So this is familiar ground for many of you listening.
And it's worth asking why they're so popular.
Yeah.
I mean, there's this constant, almost urgent drive for AI that's more robust, that can actually reason, not just recognize patterns, right? Our standard models, they're fantastic at quick, intuitive System 1 type tasks, recognizing objects, finishing sentences fluently.
Yeah, uncanny sometimes.
But they often hit a wall with complex problems needing planning or checking steps or multi-step logic. System 1 models just kind of fall down there. So these Inference-time techniques try to fill that gap. They try to add this capacity for deeper thought, mimicking those higher order functions. It's basically admitting that just scaling up System 1 isn't enough to get us to truly robust AI.
But, and this is the crucial but, these current approaches have some pretty major limitations. And this is where the paper really makes its entrance, the first big one. Many are modality-specific.
Yeah, and modality-specific, for you experts listening, means they often just work well in one sandbox, like one type of data.
The abstract mentions text specifically.
Exactly, e.g. working only in text. So think about chain of thought. It's brilliant for language tasks, right?
Game changing, yeah.
But try applying that same logic directly to get a model to reason about a complex visual scene.
Yeah.
Or deduce patterns in, say, financial time series data, or compose music. It doesn't translate easily.
Why not? What breaks down?
Well, the underlying architectures, the way data is represented, the embeddings, the very structure of the problem, it can all be radically different across modalities. So a reasoning trick optimized for text just falls apart elsewhere.
And the practical impact of that.
It's huge. If every new data type needs its own custom-built System 2 approach, well, that fragments research. It's hugely redundant, and it really holds back progress towards general-purpose AI.
Yeah, you lose that cross-domain power.
Exactly. You don't get that unified intelligence that can smoothly go from reading a doc to interpreting a picture to planning robot actions. It's a major roadblock.
Okay, so that's modality specificity. Then even within one modality, like text, there's the second limitation the paper points out. They're often problem-specific.
Right, and the abstract gives examples like verifiable domains, like math and coding.
Okay, why verifiable? What does that mean here?
It means domains where there's usually a clear right or wrong answer, a structured problem space, often deterministic results. Is the math proof valid? Yes or no? Does the code compile and run correctly? Yes or no? Did you solve the logic puzzle by the rules?
Got it. Clean feedback signal.
Precisely. Very clean signal for training, for evaluation. These are great sandboxes, really, for developing and testing reasoning. But that same verifiability becomes a limitation.
How so?
Because when you step outside those clean domains into more open-ended, ambiguous, maybe subjective tasks, like generating truly creative fiction, or making nuanced ethical calls, or even navigating scientific discovery where the truth isn't fixed.
Right, the clear ground truth vanishes.
Exactly. There's no single correct answer to train against, no simple reward signal saying, yep, that reasoning was perfect. So this really limits the transferability to messy, real-world problems where things aren't black and white. It's a bottleneck for true general intelligence.
And then we get to what the abstract flags as maybe the biggest hurdle of all. The one that really limits scaling these reasoning abilities. It's the need for additional supervision training on top of unsupervised pre-training. That sounds like a big conflict, doesn't it? Especially with how successful pure unsupervised pre-training has been for foundation models.
It's a massive tension, and it really gets to the heart of why EBTs are innovative. Let's break down additional supervision training for this audience.
Okay.
Often, it means giving the model human-labeled data specifically designed to teach the reasoning or the verification step itself.
So not just the answer, but the steps.
Exactly. Say you want a model to do multi-step math. You might need humans to label not just the problem and final answer, but every intermediate step.
Yeah.
Or point out logical flaws. Or give feedback on the quality of the reasoning. The abstract mentions things like needing verifiers or verifiable rewards.
And the problem with that is?
Think about the sheer scale and cost. For a big LLM, getting chain of thought to work well means not just scraping the web, but then meticulously annotating maybe millions, potentially billions, of examples with the correct logical step.
That sounds incredibly expensive.
It is. It's not just labeling a cat in a picture. It's labeling the process of human thought. Or in RL, designing these super intricate reward functions that don't just reward the outcome, but the right kind of reasoning steps.
Astronomical cost and complexity.
Right. It becomes this huge bottleneck for scaling up intelligent behavior.
Yeah.
And it's totally at odds with the unsupervised pre-training paradigm that's been so powerful, where models learn amazing things just from raw data.
So that's the gap EBTs are trying to fill.
Precisely. How do we get these powerful System 2 skills without this incredible, expensive, non-scalable extra layer of supervision?
Okay. So given all these challenges, modality specificity, problem specificity, the massive supervision cost of the paper, asks this really direct, powerful question. Is it possible to generalize the System 2 thinking approaches and develop models that learn to think solely from unsupervised learning?
And just pause on that question for a second. The sheer ambition there.
It's huge.
If the answer is yes, the implications are just transformative. For AI scalability, for autonomy, imagine models developing complex reasoning just by processing raw, unlabeled data. Like kids learning from observing the world.
Without explicit how-to-reason lessons.
Exactly. It unlocks a new level of self-sufficiency. It could massively accelerate progress towards a genuinely adaptable AI that can tackle new problems without needing constant human hand-holding or these massive data labeling campaigns. It's a fundamental shift in the learning paradigm, closer to systems that learn to think autonomously.
And then the paper just drops this bombshell, almost casually. Interestingly, we find the answer is yes.
Yeah, quite the statement.
A very bold claim, given everything we just discussed. So, okay, how? How do energy-based transformers supposedly pull this off? What's the core mechanism that lets them learn to think without supervision?
And that yes is really significant because it flies in the face of the common assumption that complex reasoning needs explicit supervisory signals. The key insight, the core idea behind EBTs, is that they learn to explicitly verify the compatibility between inputs and candidate predictions.
Okay, explicitly verify compatibility. What does that mean in ML terms?
It means the model isn't just spitting out an answer based on patterns it's seen. It actually develops an internal learned way to judge how well a potential answer, a candidate prediction, fits with the input.
So it's like an internal quality check?
Kind of, yeah. Like a self-trained critic, assessing the consistency, the plausibility, the validity of its own ideas relative to the input. It's different from a standard classifier just mapping input to output, or even a normal generative model that just generates likely sequences without necessarily checking them against the input in this explicit way.
The verification is baked in.
Right? It becomes an intrinsic part of how it generates and refines things. And it learns this evaluation function, this sense of compatibility, just from the unsupervised data itself. It's not just generating, it's generating and judging based on learned consistency rules.
That sounds like a really different way of framing the problem. So not just input to output, but EBTs actually reframe prediction problems as optimization with respect to this verifier. That sounds more iterative, less like a single shot.
It's absolutely a paradigm shift, yeah. And this is where the energy-based models part comes in. EBTs are presented as a new class of energy-based models.
EBMs.
Right, EBMs.
Yeah.
Quick refresher.
Sure. The core idea of EBMs is pretty elegant. They assign a scalar value, an energy, to every possible state or configuration of a system. Lower energy means higher probability, or more desirable, or in this context, more compatible.
Okay, low energy, good fit.
Exactly. It's a flexible way for the model to learn a function that just says how good or bad any input-output pair is.
And how do EBTs use this? Specifically, they assign an energy value to every input and candidate prediction pair. Think of this energy as measuring incompatibility or badness. Low energy means the prediction fits the input really well. High energy means it's a poor fit, inconsistent, maybe just plain wrong for that input.
And this energy function is learned.
Learned purely unsupervised, yes. It captures the inherent compatibility patterns within the raw data.
Okay, so how does inference work then? How does it make a prediction? This is where the system 2 part comes in, right?
Precisely. This is where the iterative refinement, the thinking happens. Predictions aren't one shot. Instead, they're made through gradient descent-based energy minimization until convergence.
Whoa, okay. Gradient descent at inference time.
Yeah. It starts with some initial guess, some candidate prediction. It calculates the energy. How compatible is this guess with the input? Then it uses the gradients of that energy function to tweak the prediction step by step, trying to lower the energy.
So it's like rolling downhill on this energy landscape.
Exactly. It iteratively adjusts the prediction, following the slope of the energy surface, until it finds a stable point, a prediction that minimizes the energy, a point of maximum compatibility.
And that iterative search is the thinking process.
That's the analogy, yes. It's like exploring a solution space, constantly checking your current idea against that internal compatibility measure and refining it until you land on something optimal, something with low energy. It's deliberate, it takes computational steps, unlike just sampling from a fixed distribution.
More effortful, potentially more accurate?
Potentially, yes. It allows the model to actively search for the best answer according to its learned compatibility rules, not just the most probable pattern it memorized. That's why System 2 thinking feels like the right description. It's a search.
And the absolute game changer here, the point we keep coming back to, is that EBTs learn this whole complex setup, the energy function, the iterative search, solely from unsupervised learning.
That is the absolute core of the contribution. No human-labeled verification data needed. No complex handcrafted reward functions. No predefined correct reasoning steps. It directly tackles that huge supervision bottleneck we talked about.
The scalability implications seem enormous.
They really are. Anyone dealing with large model training knows this. Getting massive amounts of raw text, images, video, that's feasible, relatively cheap even. But curating perfectly labeled reasoning steps or verification signals for billions of examples.
Forget about it.
Right. The cost, the time, the effort. It's prohibitive. EBTs bypass that entirely. The ability to learn this system to process autonomously from raw data just opens up completely new possibilities for training truly massive, capable models without hitting that data annotation wall. It could seriously accelerate the path to more general AI that can actually think for itself, a big step towards self-sufficient AGI.
Okay, so we have the theory. Unsupervised System 2 via energy minimization. Now, let's get concrete. Let's shift to the evidence. The abstract presents some pretty strong results, right? Across different metrics, different data types. This isn't just theory.
Exactly. Now we get into the numbers, the quantitative proof that supports these big claims about scalability and performance. This is where we see if this novel approach actually delivers tangible benefits that could impact, your own work. It's one thing to propose it, another to show it works better.
And the first really big claim that jumps out is about training. EBTs scale faster than the dominant transformer plus approach during training. That sounds huge, especially for anyone training large models.
It's a massive claim, yeah. one that definitely grabs your attention if you're working at the cutting edge of foundation models. And they quantify it. EBTs achieve an up to 35% higher scaling rate. That's not trivial. It's a really significant bump in efficiency. It could change the whole cost-benefit analysis of training next-gen models.
And this scaling improvement applies across the board.
That's what's impressive. The abstract is specific. It scales better with respect to data, batch size, parameters, FLOPs, and depth. So it's a comprehensive improvement across all the things we care about in large-scale training.
Okay, let's quickly unpack why each of those matters for our listeners. Data.
Better scaling with data means EBTs get more bang for the buck from larger data sets. They learn more effectively, potentially leading to richer, more robust models from the same amount of data, or leveraging even bigger data sets than before.
Batch size.
Crucial for distributed training. Scaling well here means you can use bigger batches effectively, which speeds up training and makes better use of your hardware, like GPUs. Squeezing more out of your cluster
Parameters.
means EBTs can effectively handle having more knobs to tune, more model capacity. This is key for building bigger, more complex models that can capture really intricate patterns, so potentially more powerful models down the line. That's your raw computational efficiency. Better FLOP scaling means more performance per unit of compute. That's huge for cost, for energy consumption. Less compute needed for the same result, or better results for the same compute budget.
And finally, depth.
Scaling with depth lets you train deeper networks effectively. Deeper networks can often learn more abstract hierarchical features, which might be critical for really complex reasoning. Allows for longer chains of processing.
So the bottom line is scaling faster could mean building more powerful models using fewer resources or in less time.
Exactly. It could make cutting-edge AI more accessible, accelerate innovation. It suggests EBTs aren't just interesting theoretically, but offer real, practical efficiency gains.
Okay, so impressive training scalability. But what about inference time? Does that System 2 thinking actually lead to better performance when the model is put to work?
Yeah, this is where that iterative energy minimization really pays off. You see the benefit of that thinking process. For language tasks, the paper states EBTs improve performance with System 2 thinking by 29% more than the Transformer++.
29% more improvement from System 2. That's specific.
It is. It suggests the EBT's unsupervised verification process is genuinely leading to better results on complex language tasks compared to how Transformer++ benefits from its own inference-time compute. It's a significant jump, implying better self-correction or refinement.
And what about that modality issue we discussed?
This is another key result. They show generalizability across both discrete, text, and continuous visual modalities. This directly counters that modality-specific limitation of older methods. It's a unified approach.
Any specific examples?
Yes, a really important one for the visual domain. EBTs outperform diffusion transformers on image denoising.
Wow, diffusion transformers are state-of-the-art there, aren't they?
They are often the benchmark for image generation and processing. So, outperforming them on a tough task like denoising is a very strong signal. It potentially sets a new bar.
That's impressive on its own, but is there more?
Yes, and this is crucial. They achieve this while using fewer forward passes than the diffusion transformers.
Okay, fewer passes is faster inference, right? Less compute.
Exactly. Anyone who's worked with diffusion models knows they often need hundreds, maybe thousands of iterative steps to get top quality. That's slow, computationally expensive. If EBTs get better results with fewer steps, that's a massive win for efficiency.
It makes high-quality generation much more practical.
Potentially unlocks real-time applications that were just too slow before. It's a breakthrough in that quality versus compute trade-off, a big step for practical generative AI.
That efficiency combined with quality is really compelling. Okay, one more major finding. Generalization. EBTs supposedly generalize strongly. What does that mean practically?
Yeah, strong generalization is always the goal, right? The abstract says EBTs achieve better results than existing models on most downstream tasks. But there's a critical nuance here.
Okay, what's the catch?
It's given the same or worse pre-training performance. This is super important for you experts to know.
Why is that so important?
Because it means the EBT isn't just doing better, because it had vastly more data or compute during its initial pre-training phase. It suggests that even if you start with a foundation model, it's only as good as or even slightly worse than a standard Transformer plus after pre-training. The EBT architecture itself enables it to generalize better to new downstream tasks.
So the advantage comes from the architecture, the unsupervised System 2 learning.
That's the implication. That internal compatibility verification mechanism seems to give it an edge in adapting to new problems, even ones different from pre-training data. It's learning more fundamental principles, perhaps, allowing for better extrapolation, not just interpolation.
And the practical benefit.
Models that work well on new tasks without needing tons of task-specific fine-tuning, even if their initial pre-training wasn't necessarily superior. That means more robust, adaptable, and maybe cheaper AI deployment. Foundational models that are just inherently more versatile. It really elevates EBTs beyond just performance bumps to something more fundamental architecturally.
Okay, so let's try and wrap this up. To summarize the really core breakthroughs here, EBTs offer a new path to unsupervised System 2 thinking. That's the big conceptual leap. Empirically, they show much better scaling during training, faster, more efficient across data, parameters, compute, everything.
Right, up to 35% better scaling rate.
Then at inference time, that System 2 process delivers big performance gains, like that 29% extra boost on language, outperforming diffusion transformers on images and doing it faster.
And crucially, across different modalities.
Right, text and vision. And finally, they show this strong generalization capability, doing better on downstream tasks, even without necessarily better pre-training.
It's a compelling package, definitely.
It seems like a pretty comprehensive set of advancements.
I think you've hit all the key points. That core answer to the paper's big question, can we generalize System 2 thinking using only unsupervised learning? They don't just say yes. They provide a concrete working architecture, the EBT, that shows strong empirical evidence for it. It really does feel like a potential shift away from needing all that costly human-labeled reasoning data towards models that can develop these internal checks and reasoning skills more autonomously.
So for you, our listener, the so what here seems pretty clear. EBTs look like a genuinely promising new direction. A new paradigm, as they say, for scaling both how models learn and how they think. This doesn't feel like just another tweak. It feels like it could really change the trajectory for AI development, suggesting a future where our big models learn to reason much more autonomously, much more scalably.
Exactly. For this expert audience, it signals a potential shift in designing and training future large-scale models, moving towards inherently more intelligent, more adaptable systems. Systems that learn to reason from raw data rather than needing us to explicitly engineer their verification steps or guide their thinking with supervised labels.
It could streamline development, maybe unlock capabilities we've only dreamed about.
Systems that don't just understand, but internally validate and refine their own understanding.
Which brings us to our final provocative thought for you to chew on. If EBTs really have cracked a scalable path to unsupervised System 2, what fundamental limits does that break? Especially for multimodal foundation models.
Yeah, and how quickly could this accelerate things? Could we see truly autonomous reasoning agents emerge faster, agents operating effectively out there in the messy, complex real world?
It leaves you wondering about AI that learns to reason much more like we do from experience from data without needing constant how-to-reason instructions.
Just learning what to learn and figuring out the how itself, something profound to think about.
Indeed, something to mull over until our next deep dive.